Hello, my name is Ilmari Oinonen and I'm presenting my master's thesis on the performance comparison of simulation models and parameters for engine CFD applications. The objective of the thesis is to gain information on how to improve computational fluid dynamics simulation quality for a given engine model through a systematic study. The posed research questions are: which CFD models and parameters have the most influence on simulation results? Do results from different metrics of performance for the engine model correlate? Which CFD model and parameter options offer little improvement in simulation results for significant increase in computational cost? How does refinement of the computational mesh, both in the bulk of the mesh and near wall layers, affect the simulation results? And do the used CFD models function consistently with their theoretical formulation? The references for the model used in this thesis are an experimental optical engine from the Imperial College and a high-fidelity direct numerical simulation based on the optical engine. In order to validate and qualify the performance of the engine model, simulation results are post-processed and a metric is defined that is indicative of the quality of performance of the model. Engines are a staple for energy production in the marine industry for over a century, and their importance in the development of the world into what it currently is cannot be understated. This has a lot to do with their inherent scalability. They can be used in many different kinds of vessels. Engine power outputs depends on combustion cylinders, the number and size of which can be varied, directly affecting the power output. Engines are also flexible, simpler to install and operate than gas turbines, and they can be created to use multiple different fuels. When developing new engines or improving existing ones, modeling is an essential part of the process. In modeling, a simplified version of the engine is created either physically or virtually. The benefit of modeling is that it allows for the testing of the engine characteristics with a smaller commitment. Large marine engines are very expensive to produce, and their development requires multiple cycles of modeling of different scales, starting from individual components up to a full engine model. Modeling always leaves some physics out of the sake of the feasibility of the model. For the fluid flows within an engine, such as combustion, fuel sprays, or flows in and out of the engine, CFD is used. This is due to the great degree of complexity of fluid flows inside an engine, which cannot be solved analytically. Here we focus on a simplified engine case with no combustion, no valve movement, and is axisymmetric, which isn't often the case with real engine cylinders. The benefit of a simpler model in this case is that it's easier and faster to get results with. This is especially important for this thesis as it allows for running a lot of different configurations and the comparison of their results. However, even a simple engine model has a lot of different models and parameters that it's using. And for that reason, some choices have to be made on what models and parameters we focus on. In this thesis, CFD is used as the method of modeling the fluid flows. In CFD, complex fluid flows that cannot be solved analytically are instead solved computationally in an iterative manner. The control volume inside of which the fluid flow is housed is divided into a large number of individual cells that constitute a computational mesh. In the case of time variable fluid flows, such as the one focused on in this thesis, the simulation time also divided into discrete time steps. The governing equations of fluid flow are solved for each cell of the mesh for one time step at a time, based on the solution of the previous time step in a sequence called time marching. This is done until the last time step at the end of the simulation time. The required number of computations scales with the volumetric resolution of the mesh for each dimension and the time resolutions. When the values for each cell and time step are calculated, interpolation is used. Interpolation produces error, which means that CFD solutions also have error. It is of course desirable that the magnitude of error is as small as possible. In this thesis, the open source CFD software OpenFOAM is used. It is beneficial to base the simulations on a case that has good reference data available. It makes it easier to validate whether the simulation is behaving correctly. Measurements from experiments are great as a reference data, as they are by definition based in reality. In this case, the experimental engine set up by Morse et al. Is used as the basis. Another way is to use an already well-validated model case as a reference. In this case, the DNS study by Schmidt et al. Is used. In CFD, DNSs are very high-fidelity simulations, of which a very wide range of data can be extracted, more so than from experiments. The engine case using this is based on the Imperial College experiment. The paper reported profiles of axial velocity that were averaged over the cycles, and the root mean squares of those axial velocities, which correspond to the cycle-to-cycle variation in the velocity. The results were reported for four different crank angles. Another reference for this thesis is the DNS by Schmidt et al. It is based on the previous experimental engine. In DNS, all turbulent fluctuations of fluid flow are resolved, which takes a lot of computational resources. The DNS is able to replicate the flow phenomena from the experiment very well. The report provides a plethora of data from the simulations, including the corresponding axial velocity and root mean square profiles and turbulent kinetic energy profiles. While experimental results are by definition closer to reality, high-fidelity simulations such as DNS can provide a much larger amount of data. For example, in this case, the experimental data was fairly coarse, unlike the DNS data. The DNS data in this case is used as the main reference thanks to its much larger resolution of data. A CFD model of the Imperial College case has been created in-house at Wärtsilä. This model is not specifically created for this thesis, but this thesis helps to assess how well it is performing compared to the reference data. The mesh for the model is created using OpenFOAM's meshing functionalities. This is done with the help of some in-house meshing tools created at Wärtsilä. The main challenge is the meshing is the movement of the piston, which changes the volume of the cylinder. Here is an animation which shows the simulated fluid flow in and out of the engine cylinder. The field data is collected from horizontal cut planes, which are placed corresponding to the reference data. The cut planes are used to sample data from the computational mesh. Two types of averaging is applied on the sampled data. Azimuthal averaging averages over the circumference of the engine cylinder and creates a one-dimensional data array from the two-dimensional cut plane data. Ensemble averaging averages over the engine cycles to reduce cycle-to-cycle variation. A mean absolute error, or MAE, is calculated between the averaged simulation results and reference data. The magnitude of the MAE is proportional to the accuracy of the simulation in comparison to the reference. In the comparison studies, the performances of the different simulation models and parameters were compared when applied to the engine model. Multiple instances of the engine case are created with different model and parameter combinations. The number of total cases is the product of the number of options and each model and parameter. for each model and parameter. All created cases are then run and post-processed. The performance differences of the cases are visualized using the calculated MAEs. The first study looked at 3 different turbulence models, 3 different mesh resolutions, 3 velocity advection schemes, and 3 maximum current numbers, totaling 81 cases. Turbulence models are referred to the method that is used to calculate the effects of turbulence on the flow. Velocity advection scheme refers to how the method of approximation when solving the velocity for individual cells. And current number is related to the time step. It's essentially equal to how many cells does a fluid element pass during a single time step. Here we have figures of the MAE matrices, calculated for average axial velocity on the left and turbulent kinetic energy on the right for each case of the study. The blacked out cells are cases that crashed. Darker color and larger number correspond to worst agreement and vice versa. Based on the results, the RNG K epsilon and K omega SST SAS turbulence models worked similarly well for fine mesh resolutions. The standard K epsilon turbulence model for some reason predicted axial velocity better with coarser meshes. The velocity advection scheme had inconsistent effects on performance. Max current number had little effect on performance, but the simulations with a small maximum current number took a lot longer to run. It is visible that the middle mesh resolution had stability issues, which wasn't expected. Here are some instantaneous flow fields, and different degrees of fluctuations can be seen here. The leftmost is the RNG K epsilon, the middle one is the K omega SST SAS, and the right one is the standard K epsilon, which has pretty much no fluctuations. It was also observed that the direction of the jet from the valve port was an indicator of performance quality. The second study looked at 3 different mesh resolutions, 3 configurations for mesh surface inflation layers, and 2 relative first inflation layer thicknesses, totaling 15 cases. Surface inflation layers are used to capture boundary layers that form when fluid flow goes past solid surfaces. It was observed that the inflation layers generated with the automatic mesh generation had some inconsistencies. It seemed that the simulation increase in all the parameters generally decreased performance. Therefore, number and thickness of inflation layers should be limited. The third study looked at 7 different turbulence models and 3 velocity advection schemes that were the same as in the first study, totaling 21 cases. For the velocity prediction, the RNG K epsilon and K omega SST SAS turbulence models performed well again. The standard K omega and K omega SST had very good predictions for turbulent kinetic energy. And the K omega 2006 had noticeably poor performance. Here are some instantaneous velocity fields again, and the other models seem to function as expected, but the K omega 2006 had much more fluctuation than expected, and it could be that the model didn't function correctly in this case, which also could explain the poor results. The fourth study looked at 3 different subgrid scale models for large eddy simulation, or less. Also 3 mesh resolutions and 3 velocity advection schemes that were the same as in the previous studies, totaling 27 cases. The dynamic K-equation and Whale models, subgrid scale models, had very similar performance in terms of velocity prediction. Finer mesh didn't perform better, especially with the linear upwind grad U velocity advection scheme. None of the less runs performed better than the best performance of the previous turbulent study. And from the instantaneous velocity fields, it can be seen that all the models have a lot of fluctuations, which is expected. To conclude, the turbulence model had a dominant effect on the performance of the engine model. And contrary to expected, many of the RANS turbulence models had significant cycle-to-cycle variation. The velocity advection scheme had significant but inconsistent effects on performance. Differences in time step length through changing the maximum current number had minimal effect on performance, but a large effect on simulation time. An increased mesh resolution did not always yield improved result correspondence. The number of inflation layers should be limited in the present type of meshing configuration. With the present configurations, less did not outperform the best performing RANS models, and the quality of the prediction for average axial velocity and turbulent kinetic energy did not always coincide. Thank you.